Good morning, students. In the chapter Structure of Atom, last time we have done with your atomic numbers and mass numbers, isotopes, isobars and isotones. Now, we are done with the Rutherford's model, we have done with the drawbacks of the Rutherford's model. Now, after Rutherford's model of an atom, the next model that was given was Bohr's model, given by Niels Bohr. But before doing the Bohr's model, we are doing what are the different developments that took place that led to the Bohr's model of an atom. That means what are the important discoveries that were made before Bohr gave his model. The two important discoveries which led to the development of Niels Bohr's model were, first, dual nature of radiation, and we will study about in detail. Firstly, it was considered that light or any thermal radiations have wave nature. Later on, it was found that no, it has got particle nature. But there were some properties which could be explained by wave nature and some by particle nature. So the concept of dual nature of radiation came. That is, radiation has wave nature as well as particle nature. As well as particle nature. We will do this in detail. And the second concept that developed was atomic spectra. The emission and absorption spectrum for different elements. So these were two important discoveries which led to the development of Bohr's model. We are going to study them stepwise. So let us start with the topic wave nature of electromagnetic radiations. We are going to study the wave nature and then the particle nature. And then we will see how the two natures were combined and the dual nature of radiation was given. So we are starting with wave nature of electromagnetic radiations. Now in the mid of the 19th century, many scientists studied the emission and absorption of radiations by heated objects. Absorption of radiations by heated objects. These radiations were called as thermal radiations. And the scientists were studying what are these thermal radiations made up of. They wanted to know the composition of these thermal radiations. Again, I am repeating, in the mid of the 19th century, many of the scientists studied the emission and absorption of radiation by heated objects. You know, when you heat anything, it absorbs the heat energy. And when it cools down, whatever energy it has absorbed, it will emit. So, the energy which was absorbed or emitted, it was done in the form of radiations which were called as thermal radiations. The nature of these thermal radiations was studied in detail in 1870 by James Maxwell. And according to him, the thermal radiations are electromagnetic radiations, or he also called them electromagnetic waves. since all these radiations propagate in the form of a wave and they are associated with an oscillating electric and a magnetic field perpendicular to the direction of oscillation. Again, I am repeating. Maxwell called these thermal radiations as electromagnetic radiations or electromagnetic wave because according to him, these radiations propagated in the form of wave and they produced or they were associated with an electric and a magnetic field perpendicular to the direction of propagation of waves. And therefore these radiations were called as electromagnetic waves. If the waves move in this direction, perpendicular to it, in this direction there is an electric field, and another direction perpendicular to it there is a magnetic field. So they were called as electromagnetic radiations or electromagnetic waves, and it was experimentally proved by Hertz. The experimental proof for electromagnetic radiations of waves was provided by Hertz. So now what are electromagnetic radiations of waves? Even light is an electromagnetic wave or electromagnetic radiation. So what it is? A radiation which is associated with an oscillating electric and a magnetic field perpendicular to each other and perpendicular to the direction of propagation of wave is called electromagnetic radiation. Again, I am repeating. A radiation that produces an oscillating electric and magnetic field perpendicular to each other and also to the direction of propagation of this radiation in form of wave is called electromagnetic radiation or electromagnetic waves. Again, I am repeating, light or any electrically charged particle which is accelerated moves in the form of waves. And this, if this is the direction of propagation of wave, to its perpendicular direction there is an oscillating electric field, and again perpendicular to it there is an oscillating electric field. So three things are perpendicular to each other. This is the direction of propagation of wave, this is the oscillating electric field, and this is the oscillating magnetic field. And these radiations are called as electromagnetic radiations or waves. Although the study of these electromagnetic radiations are quite complex at this level, but we are doing some of the important properties of these electromagnetic radiations. So let us consider with the properties of electromagnetic radiations. First, of course, we know that they are associated with an electric and a magnetic field, which is perpendicular to each other and perpendicular to the direction of propagation of wave. So they are associated with electric and magnetic field perpendicular to each other, perpendicular to each other and to the direction of propagation of wave. these electromagnetic radiations can move in vacuum, unlike the sound waves. You know that sound waves require a medium to travel. So sound waves are not electromagnetic radiations. Electromagnetic radiations can travel in vacuum, but sound waves cannot. So electromagnetic radiations do not require a medium to propagate, do not require a medium to propagate like sound waves. Like sound waves. You know that sound waves require a medium. They can travel in vacuum. Travel in vacuum. Thirdly, electromagnetic radiations are of different types. They can be classified on different types based on their frequency and wavelength. So electromagnetic radiations are of different types based on their frequency or wavelength. For example, you know some of them: infrared radiations, UV radiations, gamma rays, visible region, radio waves, microwaves. So they are the different types of radiations on the basis of frequency or wavelength. If I arrange all the electromagnetic radiations in the increasing order of their wavelength or decreasing order of their frequency, then it is called as electromagnetic spectrum. Again, I am repeating: the arrangement of different electromagnetic radiations, the arrangement of different electromagnetic radiations in the increasing order, in the increasing order of their wavelength, which are represented by the symbol lambda, or decreasing order of frequency, represented by mu. Then this arrangement is called electromagnetic spectrum. Is called electromagnetic spectrum. So let us see the electromagnetic spectrum. We are first arranging at the top in the decreasing order of frequency, varying from nearly 10 to the power 24 to 10 to the power 0 Hertz. And the wavelength 10 to the power minus 16 to 10 to the power 8 lambda meters. Wavelength in meters. So I am arranging them in the increasing order wavelength and decreasing order frequency. Clearly means the two things are inversely related to each other. If the wavelength increases, the frequency goes on increasing. The first comes the cosmic rays and then the gamma rays. Gamma rays. After the gamma rays, you get the X-rays, the UV rays, and a very small region at about 10 to the power 15 Hertz is the visible region. This is your visible region. Visible region is the only part of electromagnetic spectrum that we can see with our eyes, and that's why it is called as the visible region. It varies from 400 nanometer to 750 nanometer. The wavelength varies from this to this, and it consists of the 7 colors that you know, that is Vibgyor. So that is the visible region. After the visible region comes the IR, infrared region. After the infrared region comes the microwaves, and then comes the radio waves around 10 to the power 6 Hertz, FM, AM. And after the radio waves, here we get the long radio waves. And out of all these waves, we know that all these waves of course have got different properties. But we know that our eyes can see a very small region, that is the visible region. So this have been arranged in the decreasing order of frequency and the increasing order of wave. Now we are going to study the different properties of these radiations. The different properties of these radiations, we are starting with the properties of these electromagnetic radiations. The first property of these electromagnetic radiations, wavelength. Lambda. We know that electromagnetic radiations have got a wave nature. This is the wave nature. This is how they propagate. Now, what is wavelength? The distance between two consecutive crests, or you can say between two consecutive crests, that is lambda. So what is wavelength? Lambda, it is the distance between two consecutive crest or trough. This upper part of the wave is called crest and this lower part is called as the trough. The distance between two consecutive crest or trough is called as wavelength. It can be measured in meters, centimeter, nanometer, angstrom and picometer. These are the different units in which it can be measured. Then next is velocity. This is also a very important property of electromagnetic radiations. All electromagnetic radiations, all of them travel with the speed of light. Travel with the same speed, that is speed of light. Light, that is represented by c. Actually, it will be represented by c. V is the common symbol and c the velocity of light. 3.0 into 10 to the power 8 meter per second. So the velocity for all the electromagnetic radiations is represented by c and it is 3 into 10 to the power 8 meter per second. Next property is wave number. wave number represented by mu bar. If I consider this length to be 1 meter, now what is wave number? The number of waves, the number of wavelengths per unit length. The number of wavelengths per unit length is called wave number. That means if I consider this length as 1 meter, the number of wavelengths are 1, 2, 3, 4. So wave number is 4. In fact, wave number mu bar is equal to 1 upon lambda. So it is the reciprocal of the wavelength mu bar. Next comes frequency. Frequency. Frequency represented by mu. Frequency is number of waves that pass through a particular point per second is called frequency. Its unit is cycles per second or hertz. Same way, wave number, if I say the unit, we know that lambda is measured in meter, so the unit for wave number will be meter inverse. Now the last term, amplitude. Represented by A, it is simply the height of the crest or depth of a trough. This distance is amplitude. The height of crest or depth of trough is called as amplitude A. Now just we will see in last the relationship between all of them. The relationship between all these properties. We know that mu bar is equal to 1 upon lambda. Mu is equal to C upon lambda. Mu is the frequency. Mu bar is the wave number. So mu is equal to velocity upon lambda. And mu bar is equal to 1 upon lambda. And the frequency is 1 upon time period. So these three are the relationships that relate them, and if I know the value of any one, I can calculate the rest. The value of velocity, you know, C is fixed, and rest we can calculate from these formulas. Thank you.